Howdy. The purpose of this video is to introduce the concept of electronic band structure and band gaps. What do these terms mean, and where do they come from when we start combining the properties of individual atoms? So we know we have materials that behave very differently electronically and optically. On one hand, you have metals that are good conductors. They tend to be optically opaque and reflective. On the other hand, we have things that are great insulators, so they don't conduct electricity well, and they tend to allow light to pass through them. They're transparent. Think of something like diamond. Somewhere in between, we have semiconductors, which are sort of a combination of the two behaviors. They conduct electricity okay, and they can be transparent to certain wavelengths of light. Where do these properties come from? And it turns out that all of the properties come from the available energy levels that electrons can occupy, and which of those energy levels are full of electrons. And that's what I mean when I say electronic band structure. So how do I get a band structure? Where does it come from? And it comes from combining the properties of individual atoms. So if you remember when we talked about orbitals, we talk about discrete energy levels that electrons can occupy in a single atom. And we think of these as our traditional orbitals, 1s, 2s, 2p, 3s. What happens when we start interacting atoms together? If two atoms are very far apart, they're not going to see each other, and their energy levels are relatively unperturbed. We can consider each atom to be its own thing. It's existing in the middle of a vacuum, and it's not interacting with anything around it. As those atoms start to get closer and closer, these electron wave functions, because that's what orbitals are, they're electronic wave functions, start to overlap. They start to interact with each other. And if you think about different wave functions, they can interact constructively or destructively. So if I have two different point sources, and they're each creating waves, those waves can overlap and add up. That's a constructive interaction. Or they can cancel each other out. That's destructive. Energy wave functions, electron wave functions in atoms can behave exactly the same way. And so these orbitals will start to mix, and they'll either add up or they'll interact destructively. So let's think about the case. Let's think about two individual sodium atoms. So they have 1s, 2s, 2p, and 3s orbitals. If they're far apart, they each have their own discrete energy levels, and electrons can fill any of these energy levels. And in the sodium atom, we have 2 electrons in the 1s, 2 in the 2s, 6 in the 2p, and 1 in each of the 3s orbitals. Now, as they start to get closer and closer together, those wave functions will interact, and you see what happens. The 3s orbital starts to split into two different energy levels. And this is what I mean by the constructive. Constructive would be down here, and the destructive, higher energy level orbitals. Now we only notice this in the outermost orbitals. So in those valence orbitals, the 2p and 2s and 1s, all of these orbitals are deep within the atom itself. They're at very stable energy levels, and so they don't tend to interact with each other as much. So we don't see any splitting in these levels. So a couple things to notice here. If we start off, the total number of orbitals that we start off with has to equal the total number that we end up with. So we have two atoms. They each have one 1s orbital, and the resultant combination is going to give us two 1s orbitals. Same thing for the 2s, same thing for the 2p. They each have 3 orbitals initially, and we end up with 6. And finally, for the 3s, we have 2 individual 3s orbitals, and they split. So I have one orbital at a higher level and one at a lower level. What happens if I start combining more and more orbitals? So I'm going to really only focus on this highermost energy level from here on out. All of these core level orbitals don't interact, and they don't change. Again, we start off with 3s orbitals, and we have 4 of them because we're combining 4 different atoms. When I bring those atoms together, when they start to interact, again, I'm going to have energy level splitting. And so now I can have 4 potential orbitals that electrons can fill. If I have even more atoms, I would start off with 8 3s orbitals, which are, remember, if these atoms are individual, they don't see each other, all those 3s orbitals are exactly the same energy level. When they start to interact, they start to split. And so now I'm going to have 8 potential energy levels. So this is what we refer to as the linear combination of atomic orbitals model, LCAO. So as these atoms start to interact, their orbitals, their energy levels overlap, and in those valence level orbitals, I start to get splitting of energy levels. This happens more and more. So remember, the number of orbitals in equals the number of orbitals out. So if I start off with 50 3s orbitals, I'm going to end up with a very closely stacked series of energy levels, and there will be 50 energy levels in here. If I have a macroscopic object, something that has maybe part of a mole of atoms, maybe it's a full mole of atoms, there's about 10 to the 23 atoms that are interacting here. So I'm going to start off with a large number of 3s orbitals, and again, they're going to split, and they're going to be so finely spaced together that I could consider this to be a continuum. And that continuum is what I call an energy band. So if I looked very, very closely in here, I would see a lot of different potential orbitals, potential energy levels that those electrons could occupy, but the separation between them is very, very small, such that if I'm measuring them with any sort of realistic measurement system that I could think of, there's no way for me to separate out this energy level versus this energy level. And so that's why we think of them as this continuum, this band. So when I'm talking about an energy band, I'm talking about a large number of very closely spaced energy levels. That was a sodium atom. In that case, we're thinking about mixing together only these 3s orbitals, and they lead to one continuous band. It gets a little bit more complicated as we think about some of the traditional semiconductors. So something like silicon is going to have 3s and 3p electrons. And so these are both going to be valence orbitals. So when I start combining silicon atoms together, an individual atom will have 3p levels and 3s levels. Remember, there would be 3 orbitals in the p case, 1 orbital in the s case. When I combine together many, many atoms, these are going to all mix together, but the result actually gives me 2 continuous bands with a small separation in between. In a semiconductor, I would call this the valence band. I would call this the band gap, and oftentimes we abbreviate that E sub G, band gap. And I would call this the conduction band. And we get this separation between these 2 bands because I'm combining 2 different kinds of orbitals, and they're interacting and they're mixing, and they lead to 2 continuums, 2 bands, and a gap in between. Now in the next video, we're going to talk about how we fill these different bands and how that leads to metals and semiconductors. Okay, so the purpose, what I want you to remember from this is that we have valence orbitals. They're interacting with each other. They result in creating these energy bands. And so a band is a continuous energy spectrum. So I'm plotting on the vertical, I'm plotting energy, and there's no real meaning to the horizontal axis. But there's a large number of energy levels in here that they're close enough together that I can't separate them out vertically. And I call that a band. In semiconductors, I end up with 2 different bands, the conduction band and the valence band being the lower band. And the space, the forbidden energies between that is the band gap. All right, thanks.